Okay, so last time we talked a little bit, just some general comments about 2D problems. So we're going to go ahead and work with, or write down a model problem that we'll work with as we develop the weak form and other things, just like we did for 1D. So model problem here will be So I wrote that all out, but if we were to use vector notation, then you would recognize that this is the divergence of a tensor A times grad U, right? So in this case, U is a function of X and Y, and the Aij are the data.
That is Q not UV?
Here?
Yeah.
No, this is A00.
Okay.
Yeah. So, everybody should recognize that imagine I replace the A with a K, right? And essentially that's the Laplacian term in the diffusivity equation, right? So this is the same equation we could use to model so I'll say models heat transfer, irrotational flow, of an ideal fluid, and groundwater or single phase flow through permeable medium. So let's go ahead and develop the weak form for this guy. I'm going to multiply on the left by a test function. For compactness, I'm going to write for a moment what's in those parentheses is just F1. F2, we're going to integrate over X and Y. So in this case again, F1 is equal to So now we're going to, the reason I wrote those F's is so that I could show you what the integration by parts formulas are in 2D. So we're going to integrate by parts. So if we start with the product rule on this term, we expand it, we have this. Which we could solve for the term like this. So there's a similar expression for the F2, the term involving F2 and the dy's. So we'll use those identities. We'll substitute the right-hand sides here and for the left-hand side terms into the expression above. Right? So where we have partial x, del u partial x f1, this term, right? We'll replace it with this. Okay. And likewise for f2. We'll also use the divergence theorem so we have a volume integral that looks like this. Over dx and dy. We can replace that with a surface integral over the boundary. We'll use the and likewise for the other term involving F2. Where nx and ny are components of the unit normal to the boundary. So for example, if we have a unit normal vector defined by, then it's like nx ex plus okay, so if we plug all that in, the integration by parts formulas and the divergence theorem, then we have That's the volume integral, and then you have the surface integral contribution. And often what we'll do, well, not often, what we'll do is we're going to define this thing to be Qn. So this is a flux coming into the boundary, right? And so this is our natural boundary condition. Remember when we developed the weak form, there's 3 steps. We multiply by a test function and integrate over the body. We integrate by parts, and then we apply the boundary conditions, right? So this surface integral right here is over the boundary. So it's this term right here that would be a flux coming into the boundary. So I think what I'll do now is I'm just going to go ahead, right? Everybody should notice that, right? Well, let's see. Remember we have this bilinear operator that's a function of del u and u, right? So what we want to do is we want to grab all the terms that involve both del u and u. So that is essentially those terms. This is equal to and then this guy plus those guys will be equal to L del U. So I'll just write what those are. And then we're going to just solve the equation. And then we'll just note that B is symmetric if A12 equals A21.
Professor?
Yep.
That L del U term, shouldn't it be minus of integral del U f dx dy?
Yeah, I see what you're arguing, but if it's LU in this equation, then I moved it over already. Right?
I mean, from the previous equation.
Yeah, I know, but yeah. So if I put a negative and a negative, then I need to write B del U minus LU equals 0. Right? I moved it over to the right hand side, which flips the signs on those. So if these two definitions are associated with that equation, then that's right. You understand? Yeah. Yep.
The brackets with the del U f, the closing bracket, what
dx dy on the other side of it.
del U f?
This one?
Yeah, there is a bracket there.
Bracket just to indicate that whole thing's in the integrand.
Also from the beginning.
Yeah, I guess I should have another bracket here. Yeah. Okay, let C equal to A11, A12, 0, A21, A22, 0, 0, 0, A00, 0. And D, which is going to be an operator matrix or vector, is going to be so for example, if I write D of U, that's going to equal partial U, partial X, partial U, partial Y, U. Everybody okay with that? So B of del U and U So that is just, hopefully you can see, this is just rewritten, that equation in matrix notation. So then, using our definitions above, we have that d of del u transpose times c times d of u dx dy. Hmm? Sorry, what?
I mean, you want with du dx, du dy, and 1. Told you use.
Oh, you mean it should be u here?
Yes.
I think you're right, yeah. Yeah, because you have del u, so yeah, that should be u. Sorry. Yep. So yeah, then L So this is our weak form. So then